Our next speaker in this area, Dr. Vladimir Kolesnikov. He's a member of the technical staff for Nokia Bell Labs. He's going to be speaking to us on private database searches at scale. A little bit first about Dr. Kolesnikov. He received his PhD in computer science from the University of Toronto in 2006 and has research interests that include key exchange, secure multi-party computation, foundations of cryptography, and network security. His work is connected to the practice of cryptography, and he has worked on private databases securing channels in smart grid and WiMAX, biometric authentication, digital rights management, and a variety of other subjects. He's published his work in top cryptographic and security conferences and journals, and has served on program committees of several international cryptographic conferences, supervising several interns at Bell Labs as well. He's an editor of the WiMAX Server Certificate Profile and Device Certificate Profile Standards documents, and part of his work has been sponsored by IARPA and Korea's Gashon Energy Research Institute. It gives me great pleasure to turn the floor over to Dr. Vladimir Kolesnikov.
Thank you. If I knew that you're going to read the whole bio, then I would have made it a little bit shorter. Okay, so this presentation will be a little bit on a crypto-technical thing, but I really eliminated all of the technical things as much as I could from this presentation, so it should be mostly understandable. If there is a part of it that is missing, but it will recover and in the end. So the problem that I'm talking about here is a little bit different from cybersecurity. It's more about information sharing and the private information sharing. And I'll start with motivating. I'll start with explaining what it is and then motivating why today you want to share information in some private manner. So this is a project that was came out of U.S. intelligence. So IARPA is intelligence ARPA. It's part of the Office of the Director of National Intelligence. We won a big grant to work on this, and this is the presentation of what we have achieved in that. Okay. So what is the problem? The problem is that there is a database of private data, and there is a private query. Okay, so neither the client is not allowed to release his query. It is a secret query. Think of it of NSA asking something of the database. The database information is also private. Think of it perhaps of some protected personal information owned by the airlines, perhaps, or maybe it's another government agency that is storing this information. For example, DHS might be having a list of arrivals, departures in the country. Right, and these two agencies, these two players, they want to give access, or let's say in the database case, one agency wants to give access to its data, but the other agency cannot grab this plain text data, and at the same time it cannot tell it what it is looking for. Okay, and we want to do it fast. We want to do it as fast as possible to plain text databases. So the IARPA was requesting high performance. So this is kind of the example of what they were looking for, just to give you the picture of a scale. 100 million records, 10 terabytes data, and a rich query support. So you could do reasonable types of searches. And they wanted to be close to performance of the MySQL. Okay, so from here it seems like a little bit magic. So when people think about cryptography, they think of data encryption. But it turns out, and this is what I'm talking about, that you can do actually a lot more, amazingly a lot more, kind of like build those magic boxes where some hidden stuff goes in the boxes and then you magically get the answer. Nobody learns what happened, but it works correctly and efficiently. And so there's just some examples. They're a little bit made up. Some of them are maybe, we didn't know because it's intelligence. Some of it is intelligence work, so we didn't know exact applications. Some of it are applications from business. So a very natural example is a no-fly list. So there is a personal information of airline customers, and the government agencies they wanted to cross-check it with their databases. So the query, the names of the persons, or maybe some other descriptions that the government is looking for, is really a very highly protected question. So you cannot just say, give me everything that matches what you have, right? And at the same time, there's a contradictory kind of requirement where the data that the airline has, you really want to, for PR reasons and for other reasons, you want to keep it as private as possible and not give it to the government. So today, what is happening is that the government is collecting all this information, but I think that they could get access to a lot more rich information if they guaranteed the privacy of that information, in the sense that it was delivered to them in encrypted form, that only very special types of queries were allowed. Actually, we are low on time, so maybe I'll skip the examples, but I can explain those maybe later if I have time, or you can catch me. But I think sort of the bottom line here is that there is a lot of private information. It is probably today it is most natural to think of governments and government agencies having this private information, but another type of information is that legislation protected information that you cannot give to other players, and you want to query that information where the query is also private. Okay, so this is our architecture. The server here is a player that owns the data. He's going to he's going to kind of encrypt the data in some form and put it on the index server that is over there, and then the client will talk pretty much just to the index server. So the index server has encrypted information only. The client talks to index server in some encrypted ways only. Okay, and the server doesn't see any of this traffic, so the server doesn't know what is going on. And because both index server and the client, they only see encrypted information, except, well, the client gets the output in plain text. Then everything is protected, and we have formal mathematical proofs of that. When you're talking about, so since the index server, for example, doesn't know anything about what is being asked, there is a potential for violating the access policies. So we take care of that by having another entity. It could be, for example, operated by the server, a query checker. And the query checker ensures that only queries that are authorized by the policy can be run by the system. Okay, so this so far was description of what we do, and now I'm getting into how we do it, and then after that I'll get into kind of performance results. Okay, so a very core part of this is what we call secure computation or secure function evaluation. And I don't have time to explain how this works. I just have time to say what it is at an extremely high level. So if there are two parties, let's think about two parties. There's a application, or there's a lot of work that you can do it for multiple parties. But for us, we just need two parties, and it's simplest to think about it this way. So two parties have private inputs, A and B. So in this case, you can think of maybe Alice is the client of the database. Her private input is the query. Bob is the data owner. His private input is B. So right, and what the secure computation does is that it's a way to run some kind of protocol, and I'm not going to tell you what it is. It's pretty efficient. I give you a flavor of how efficient it is. You run some protocol, and by basically exchanging encrypted information between each other, and in the end, the players learn some function that they've agreed upon of the private data. And there is a guarantee, there is a formal guarantee that you can mathematically check that you cannot learn anything additional other than just the output of the computation. Okay, so you can think of the function f here being the search function. for example, in a database context. But of course, you can generalize it to any kind of function that you want, and there's many interesting functions that are useful in practice. And the new fashionable blockchain also can benefit, the way that how you use the blockchain can benefit from it. And the reason why I mentioned blockchain is because that buzzword everybody knows. And this thing maybe not so many people heard about. Okay, so it is efficient, and this is all I want to say, how efficient it is. If you think of function f, and you don't think of it written in C, think of it as implemented as a Boolean circuit. So if you, in computer science and engineering, you know what a Boolean circuit, you can compute some functions. So the cost, so today on a laptop with a LAN, you can compute 2 million Boolean gates per second. So this is reasonable performance. To give you a flavor, that encrypting something with AES is about 5,000 gates. So you can encrypt, for example, if I have the key and you have the data, then we can encrypt using these techniques without me giving you the key and without you giving me the data. We can encrypt 200 things per second. It's reasonable. A lot of the time you need just a few. For example, if you do financial transactions, you only need to encrypt just a couple of things to authenticate your transaction. Okay, so I believe that this is possible, right? So what's next? So you can apply that to searching already, right? Except that it will not scale to big data. So the circuits, the Boolean circuits that actually you would need to run, to generate and run on the big data, they're far greater than 2 million. And it does not scale to the data sizes that we want to operate in practice. So what this work is about is how to take this basic primitive and maybe massage it a little bit and then use it in the right way to build a bigger system that meets the performance requirements and at the same time gives you security guarantees that are formal, provable, and understandable. Okay, and so our approach is that, okay, so we have to compute this large function of computing on encrypted data, on an encrypted database. And so the approach is that we look at what this function does, how the search function does its job, and then we see where is the private information that we really need, right? Because both players submit the private information into that function after they compute, right? So we want to look at where this private information, like where this information flows, and see where there is really this is really most critically, most of it is concentrated. And we isolate those things and we evaluate those securely. And where there is very little information that is only, you can mine it and maybe you can learn something, but it's really not, probably not that much, then that part we can evaluate with less security or with no security. As a result, we can eliminate almost all of the hardness of the computation. And it's really much faster than applying this tool that I mentioned earlier. Okay, so this is, now I'm switching for the next maybe 10 minutes or so, 15. I'll talk about a little bit in more detail how exactly we look at what this the search function does and how we extract, like where is the core of the privacy information and how we manage it. Okay, so natural trade-offs, like this is the examples of what we can give up here is that we encrypt data with a deterministic encryption. So that makes our life a lot easier in our encryption. So normally, if you're not a cryptographer, this maybe is first time you hear this, what is deterministic encryption versus regular encryption. The difference is that deterministic encryption means that if you encrypt the same thing twice, your encryption will be the same. right? So, and that's a very weak form of encryption because you can tell that those things are encrypted the same. Like for example, in a very poor use case, what you could do, you could encrypt English text, each word separately with deterministic encryption. Everything is encrypted, but at the same time, you know that this word and this word are the same, and you can see the patterns very clearly, and a lot of the time you can extract a lot of information. So we try to do the right thing here, that our patterns are hard to understand, but so deterministic encryption is one thing that we do. You can tell that this is a little bit of an academic talk. And so this generates, in particular, access patterns. And in general, and I'm not going to get into details, we thought really hard about how you can try, how much you can get rid of the access patterns of what are the patterns when you participate in these protocols, what data points you're accessing. We could eliminate some of these access patterns, but in generality, we proved that it's really expensive to avoid, and it's not going to meet the engineering requirements that people want today. So we give up on that. Okay, so how do we actually do this? The second basic tool that we use is a Bloom filter. Bloom filter, again, computer science people should have heard about it. It's a data structure that allows you. It's a data structure that presents a set of data. You can throw data into this set, and later you can check if an element is in this set or not. And the way you do it is that if there is an element, you apply hash function to it, and that gives you several random looking locations. And what you do, you're going to put a 1 in the locations that hash function tells you. And then later, for you to check if an element was inserted or not, you again hash that element, and you see if there is a ones in all of the positions that this hash is pointing to. And you say that, okay, if there are ones in all of the positions, then the element was probably inserted. And if there is at least 1 0, then the element was definitely not inserted, because if it had been inserted, then there would all be ones. Okay. So what we do, okay, so I'm going to give 2 iterations or 3 iterations of what we do. So the most naive way to implement a database system using like this is, okay, it will be on the next slide. So think of this Bloom filter as a storage place for keywords that you're looking for. Okay, so what you're going to do, the data owner will create Bloom filters and will encrypt them with the key, give the key to the client, but not to the encrypted server. And he will insert the keywords into this Bloom filter, encrypted keywords. Okay, and then how will the search proceed? So think of, on the right, this is a database. The database has encrypted records and sees a client as is a server. The client will compute the set of Bloom filter indices corresponding to the keyword that he is looking for. Let's say looking by social security number, right? So the social security number, specific social security number, will correspond to a set of indices. It's encrypted, so the server doesn't know what social security number is being queried, right? It only knows the indices. And then you just go one by one through entire database, and you see if there is a match. And each record will correspond to a Bloom filter. So a Bloom filter corresponding to a person with a SSN 00001, right, will have a Bloom filter that have the 0001 inserted in it, right? So if there is a match, then you know you can return that record to the client. Okay, and so the reason why S doesn't know what happened is because, I didn't say that, but the database that he sees is a randomly permuted database. So he's returning some record, but he doesn't know what this record means. It's an encrypted record, he never saw the encryption. And he doesn't know what was asked because these were just some indices that correspond to an encryption of the SSN. So he doesn't, he cannot try different SSNs, for example, to see which one matched. Okay, so this is fine, but this is a very trivial kind of search. It's a single term search. So this is how you send the data, all right? And sort of the next step is we want to run a Boolean formula. So we want to do an arbitrary, we want to evaluate in our query when we say select star where, right? And there'll be, so in the where part, we want to put an arbitrary Boolean formula that you can evaluate on your data. And this slide kind of explains what, how we are going to do that. So the idea is that, right, and so the one property that we want to do here is that, for example, if there is a match, you wouldn't know which terms of the formula matched. You just know that there was a match, but you don't. If you have, return where A or B, right, you would return this, but you wouldn't know A matched or B matched. Or looking the other way, if there is a query that says return me everything where SSN is in this range, or maybe and the phone call was made in this range, right? And if the records were not returned, you wouldn't know why, whether it's because the SSN didn't match or the phone number didn't match. So that wouldn't work with the previous example, because the server, by looking which bits were set in the Bloom filter, he would know which of the keywords in the formula would match or not, right? So here we're adding a very strong layer of protection on that, and this is how we do it. So this blue one, there's no mouse over there. Okay. So the one on the top is the real Bloom filter, BF. What we do, what the data owner, what will do, it will choose a random pad, and he will give the random pad to C, and you can compress it in a very strong way, so that's actually very short. And he will do an XOR operation on the Bloom filter and the random pad. So now what S has is masked, and when he's checking a position in a Bloom filter, in the previous slide that I was showing you, he knows that there is this position is set to 1. Now, because it was masked with the random string, he can check it, but he doesn't know what it is, right? It's 0 or 1. If he sees a 1, it doesn't know what it means. It can mean that really the BF was a 0, right? There's no information. This information, theoretically, there's absolutely no information in this. Okay, and then what happens next? Remember that magic box that I was talking about, secure function evaluation. We're going to apply it here. Okay, so we're going to compute a function, the following function, and this is a simple function. That's what we're doing. We're reducing a huge function of searching on big data to a very simple function on searching on just on comparing just a few bits, and this is kind of at the core of our of this database system. Okay, so the client's input into this magical box will be this random pad, or actually part of the random pad that corresponds to his selection bits, that corresponds to all the keywords. And the input of the server into this magical secure computation will be the bits that correspond to his input. The bits that correspond to the positions that client told him to look up. So the server doesn't know what those bits are, again, right, because those are masked. But what do we do? First thing, inside the secure computation, we take off the mask. It's only a couple of XOR gates. It's nothing. All right, remember, you can do 2 million per second. You're taking off a couple. Actually, XOR gates are free, using some techniques that I did, actually. Okay, so you take off this, and then inside the secure computation, you're going to see this Bloom filter indices. Do they correspond? Do they satisfy A or B? So this is the example. Let's say we're looking for select star where A is true or B is true. Okay. So we look which indices A corresponds to inside this function, which indices B corresponds to. It's very easy to isolate in a very small circuit. And so in this case, the output will be 1 because A is set to 1, because the positions that A is looking for, they correspond to 1. But the secure computation functionality of this box, the boundary, guarantees that you really have no idea what happened. You know the output, but you don't know why you got this output. Okay, so this is a very strong guarantee. And here we achieve it for cheap because we are running it on a very small function. Okay, so that's great. Now we can check for each record. We can check complex functions, Boolean formulas, and nobody knows anything why this was selected. But still, there is a huge problem that so far we are going linear sequence through the entire database. This will not work. This will only work for tiny databases. So the next thing, and the next idea, it's simple, well, at least in retrospect, is that we're going to build a tree of these Bloom filters, and we're going to traverse the tree searching for what we're looking for. So we're going to start at the root. Oh, right. So what is this tree of the Bloom filters? Oh yeah, this works. All right, so this is a permuted database of records, and at each record there is a corresponding Bloom filter that contains all the keywords that are associated with this record. So in this case will be maybe an SSN, date of birth, if you're talking about person citizenship, if it's a DHS records, maybe date of entry to the country, authorized stay, all those things, right? Those will represent them as appropriately as keywords, and they will be in this Bloom filter corresponding to this record, and so on. And then what we do that in a parent in the tree will have a Bloom filter that has all the keywords of the children, and so on and so forth. So the root of the tree, for example, will contain all the keywords that are there in the database. So the root will be much larger than these Bloom filters. So the Bloom filter is not magical data structure. You have to pay based on how many elements you're inserting there. But for the typical databases, for personnel databases, for example, it's not going to grow that much because names often repeat. So if there's 1 million people here, and then let's say 1,000 of them are Alice, right? You're going to have only one entry for Alice here. Right in this big Bloom filter, and there will be 1,000 records with Alice over here. So the point of it is that there is a storage cost for this, but it's manageable. So for our 100 million, to give you an example, for our 100 million records database of personnel records, we needed about 100 megabytes of storage. We need fast access to this, so we wanted it in RAM, so we had to run it on a computer with 100 gigabytes of RAM. But today this is reasonable and affordable. And further, you can farm out. You can have smaller machines with less RAM. Okay, so what happens when we do the actual computation? We start from the top and we see if the formula is satisfied on the top. And let's say, so in this case, yes. Well, you can't really tell which ones are red, which ones are green, but there's double circles. All right, and so then, okay, if it's satisfied on the top, then we proceed with the children. And then we check this child and we say, no, the formula is not satisfied. So that's it, we truncate, we don't traverse this tree anymore, the subtree anymore, and we focus on this subtree. And we go on and we go on, and we end up at the leaf. And the leaf we check, and if it's satisfied, then the leaf, then the record is returned to the client. Okay, so what happened here? The server doesn't know why he's selecting, why this child met the policy or met the query or not met the query. All he knows that this is how he traversed the tree. Actually, that can also be hidden at an extra cost, but that's way too much to discuss here. So he just kind of knows that some patterns of exit information, and nothing else. And so the question is, what do these patterns mean? And we thought really hard about it, and it's hard to tell. So far that we could tell is that some use cases, these patterns, we can construct artificial or maybe use cases that are based on kind of potential usage. We can construct some use cases where this leakage would have some maybe significant privacy violation, and we construct some other very reasonable use cases where almost certainly this is not a lot of that this is acceptable. This kind of leakage, the pattern leakage. Okay, so this is kind of repeating what the security guarantee is, that the server basically learns the query patterns. This is like slightly different variations that emphasize different aspects of what is being leaked there. Okay, so there are some subtleties, and let me skip the subtleties and go to performance, and then if we have time, then we can return to that or to further motivations. Some use cases are pretty interesting, and also I'll be interested to hear what use cases you might come up with for this. So this is the database that we had. So this was a database of size 10 million records. Database of insurance policies, like auto insurance policies. This was run on LAN with large RAM machines, meaning 100 gigabytes. So really only this encrypted server needs to have 100 gigabytes. That's the only machine that needs that amount of RAM. The other machines can live with regular 8 gigabytes or something like that, something very standard. Okay, so these are the types of queries from the very simple one, a single keyword, just give me all Jeffreys. And then this one is a more complicated one. Give me all the Jeffreys over a certain age. So actually, equality tests in this database are much simpler and much faster. So this is because we're doing a comparison test. That's a lot more expensive, and this is representative of the cost. Queries 3 and 4 are kind of silly if you think about it, because we repeat this test 2 times and 3 times. The reason for that is that we on purpose do not optimize out that this is really the same formula. So what this results is that the circuits, remember the circuits that we're evaluating inside the secure computation, they will include 3 copies of the number comparison. So this circuit will be 3 times larger. So the number of results, everything else, the traversal patterns, everything else will be the same. So this allows you to measure the effect of the complexity of the formula, to purely extract what is the effect of the complexity of the formula on the performance. Okay, the query number 5 is the kind of more complex because it uses this like keyword, which I forgot exactly. Oh, I think this any character can be here. And then there's even more complex, I guess, 6. And the simple conjunction is 7. Okay, so this is the numbers, but I can go directly to the performance. So query 5, that was, I forget. So I guess that's the most complex, and that took longest. I will say in the end kind of how we can deal with that. But other queries are reasonable. So this is not super tightly optimized code. This was done as a fundamental research, kind of. So the code was written by students, and we focused on proofs and correctness, and that everything is secure rather than extremely tightly optimized. So there is a lot of space here to make these numbers much bigger. And in the end, I have some slides explaining that. So this gives you a kind of a range. And remember, this is an 100 million records database. So this is real life, big company kind of database that you can operate on. To give another angle, so this is how much the query took, right? But there are many matches, and actually returning those matches was a big expense. And if you look back, so think of it as a different way. This is the numbers that show you how many records per second you return. So the first column is 1,000 records. This is just a simple one. It's just look up by name. Like, I mean, normally maybe it's SSN. Maybe nobody cares to get all the Jeffreys, right? But this gives you a flavor. So if you're looking for something specific that just one term, you're going to get stuff very quickly. So 900 records per second, humans cannot process. So your analysts will not be able to keep up with this for sure, right? But even the slowest query, number 5, that we had, even that query returns almost 100 records per second. So that too, right, gives you a much faster rate than human analysts can deal with. Okay, so this is some internal kind of information that helps analyze what is going on. This slide also kind of internal. I'm going to skip that. So I mentioned that there is still a lot of room for improvement. The bottleneck for our executions were the bandwidth, the LAN bandwidth. We didn't use all the LAN, so if we tighten our code, we can have 50% improvement just from that slack that we are not able currently to fill the pipe. Then if we go from 1 gigabit to 10 gigabit link, it's not going to give you, just by using different hardware, it's not going to give you 10x performance improvement because there will be other bottlenecks. So it will be CPU bottleneck and memory management will become very critical. But I think 5x, maybe 8x should be possible. 10x with a lot of work, I think also should be possible. We can also double this by using full duplex because Ethernet, the way that Ethernet works is that you can send data simultaneously in both directions, and right now these numbers don't take that into consideration. And then there is algorithmic performance improvements, which we can also, and we have some ideas how to do that. Again, this is referencing to some academic work, but it's possible to further improve how we do this. So this core box of secure computation, there's some improvement. There's constant work by several people, including me, how to make that box much faster. And so whatever improvement goes there immediately improves our work because it's just kind of we plug it in. Then this secure computation that I mentioned, it solves all any kind of circuit that you want, but perhaps here definitely here we're using very specific circuits, and we can improve based on that. And there's several other improvements, and so total, to sum it up, without even this feature, which is, okay, let me just say, because I think it's important. It's trivial from a security perspective, but it's very important from an operational perspective. If you know what you're looking for, you're always going to be looking for a conjunction of first name, last name, then just create a column that says first name, last name, right, in your database. And now you don't have to look, because conjunctions are quite expensive. They're expensive in a database, in the regular plaintext databases, but it's particularly expensive in our database because of how it scales. So if you do this, if you know this information and you can build your database with the knowledge of that information, you can have humongous advantage. I mean, 10 to 1,000 here is just a number, it's a random number. It can be up to 1 million. The performance improvement can be huge. It really depends on the size of the database. So, but even without this optimization, we're looking for about 100 times faster with significant engineering work. How am I on time? I think it's just about my time, yes. Yeah, that's why I skipped all the things to get to this point. Okay, so with that, I will conclude and we'll take questions. I think we have maybe a few minutes. Thank you.